This is lesson 7.2, and I'm going to be going into exponential derivatives, but ones with any base. Because in 7.1, we actually talked about a specific base, which was Euler's number. This time, a is going to be anything, okay? And so I'm actually going to be going into a lot of properties of logarithmics. And so if you don't remember like log properties, you might want to watch a video from my MHF 4UO playlist, which is the advanced functions playlist. Just watch a couple log videos first and kind of get the hang of log properties again, because I'm going to go into this video as if you already know it. All right. So getting into exponential functions, you see y equals a to the power of x. If I'm going to convert that instead of in exponential form to log form, it's going to look like, I think it's log a with a y is equal to x. Yes. Okay, and since I'm taking the inverse, I'm then going to invert the x and y, and I get something like this. Okay, now what I'm going to do is I'm going to show you each of these original functions. I want to then do the inverse. Okay, so the inverse is, this one is going to be log with the base of 2, and then x is over here, right? Because a is 2, and that's what I'm going to put right over there, and then the x and the y are just wherever they were. So log, obviously, of 3 with the x, and this one's going to be log of e to the x. And so the reason why I'm showing you this is because there is something very special about this bottom one. Okay, so this bottom one is when your exponential function has a specific base of e, you're going to get this guy right here. Okay, and that guy right there we can rewrite as something called ln x. And so you should have like a button on your calculator that has an e, you should have a button on your calculator that has a log, and you should also have a button on your calculator that says lawn, as in like, you know, like you're mowing your lawn. Okay, so we specifically use ln x when we talk about log with the base of e. Okay, now what does this actually look like? On the left-hand side, you have an exponential graph, and in this case, your exponential is going to be e to the power of x. Okay, so it should look like an exponential growth because we already know that e is a specific number, which is this, and it's going to grow exponentially. Now the inverse will be something called ln. Now last semester, or when you did advanced functions last, you'll notice that, or you should recall, that the exponential inverse is a log graph. Okay, now again, instead of writing log with the base of e, we're then going to call this ln. And so like it should still look like a log function, we just call it a different name. Algebraically, it has all of the same properties as logs do. So for instance, I'm just going to go over a couple of them. If there's two things multiplying each other inside the bracket and you're taking the ln of everything, you can split them up and add them. Same with if you do division, you can split them up and subtract them. These are the same properties of log. Now, ln to the e to the power of something, you can always pull that down and multiply it to ln e. If you put two lns and you divide them, then it doesn't actually mean that you're subtracting like this. It also doesn't mean that you're subtracting like this. All it means is that you're actually just doing the division of both of them. Okay, actually maybe I should go through all these. Okay, on the other side, ln e is the same as, remember how like ln x is log e to the x? So if this x is an e, that means this x is also an e. So the way that logs had worked before with the properties is the base to the power of this number will equal this guy. Or at least that's how I remember it. Okay, now the other thing about lns is e to the power of ln x means that you actually can convert this to log e to the power of x. And so if you take e to the power of log e, so the same base to the power of x, 2x, your answer is just whatever was actually over here. And so a shorter way of doing that, or thinking about it, is if you have e to the power of ln to something, whatever that something is going to be your answer. Okay, now we have ln e to the x, and so you can bring that x down in front, and then you have ln e, and since we know already from this step that ln e is 1, we can get rid of it, and we already know that this guy is actually going to equal to x times 1, which is just x. Okay, and some of the stuff you'll recognize and you'll think about maybe for a second or something, but you'll recognize and memorize, and you won't have to memorize all these steps, it's just you'll get used to it. So if you see something like this, you'll automatically know this is just 1, and so the answer should just be e. Or that this also is log to the e base of 1, and so e to the 0 will equal to my 1. And so my answer has got to be the 0. Okay, so I think the first thing we should do is just fiddle around a little bit with e to the power of something, ln. Just make sure that we understand how our calculator works before we get into simplifying and derivatives. So the first one says, calculate what e to the power of 6 equals to. Find that button e on your calculator, do it to the power of 6, and I get approximately to 3 decimal places, 403, 3 decimal places afterwards, because we did say that it was a rational number that just keeps going on and on forever, so we're going to have to round it. You can also plug in ln 5 into your calculator and you'll get an approximate answer, 1.609. Okay, so this is just playing with your calculator. Now, we're going to start solving and using algebra. So solve for x using ln. That means that I have everything in exponential form and I want to put things into ln form. So just like logs, I'm going to ln both sides. So you treat them just like logs. All right? And just like logs, you could have brought down this x value and is now going to multiply ln e. Okay, now the x is no longer in the exponent, which is great. It's now lower as a coefficient or variable. And so what I can do is I can solve for x by dividing ln e out. And you get x equals, and you should recognize that ln e equals to 1. If you don't, you can just put this all into your calculator and you'll notice that you still get ln 5, okay, which is approximately 1.609. Okay, now let's just say that we did decide to do logs on the other side. We can still do lns, it's the same thing. And so if you just do ln or you did log, if you did log, it would just be log e 4 to the power of x, log e to the 19. But I don't really prefer to do it that way. I mean, that is technically what it means when we decide to do lns, but why would you add an extra step when you can just do ln of both sides? Okay, so same thing. Bring the x down. X is going to multiply ln 4. Okay, now I don't know what ln 4 or ln 19 is, so I'm just going to do the same thing I did on the other side and divide both sides. And so I get approximately about 2.124. Okay, now let's just practice a little bit more simplifying before we get into derivatives. Okay, now this actually requires you to remember some of the properties. So this is ln root e, and we're just going to simplify, and then we're going to find the answer. Okay, so I would actually like to write it as the exponent because that allows me to bring it down, which is much easier. 1/2 ln e, and those guys are multiplying. So remember, ln e equals to 1, 1/2, times 1. That was one of the properties, and that means your answer is 1/2. If you were to put this all into your calculator, I mean, you would get the same answer, you just wouldn't have showed your steps, and so you might lose some marks on a test. And let me write this a little bit bigger. This one is ln e to the negative 5 ln e. Okay, so we recognize right away that ln e is going to equal to 1. So equals ln e to the negative 5 times 1, which is ln e to the negative 5. Okay, and we can bring that negative 5 down, right? And multiply the ln e, which is, again, this guy is just going to be 1. So your answer is negative 5. All right, and again, I'm just going to write this a little bit bigger. E to the negative ln e. Oh boy. It's like a inception kind of thing. You have a ln e inside of a ln on top of an e. Okay, so we already know ln e, that guy's going to equal 1. Equals e to the negative ln times 1. Well, not times 1, it's just of 1. Okay, now this guy right here, ln of 1, we should recognize that from the properties, that equals to 0. Equals e to the negative 0. And anything to the power of 0 is 1. So your final answer would be 1. Okay, so the easier you guys can recognize these rules, the better it is for you. So writing this out so that you guys can see it, this is ln of e to the negative 2017 times ln 1, and then multiplying, I'm sorry, I can't squish that in, multiplying 2018. Okay, let's erase that, I'll write it nicer. Okay, let's write it over here, equals ln, nice and big, e to the negative 2017 times ln 1, 2018. Okay, let's simplify this a little bit. Again, I would expect you guys to recognize that this is going to equal 0. Ln e to the negative 2017 times 0 to the power of 2018. Okay, that's ln, what am I trying to spell? I'm trying to spell limits here. E to the power of 0, right? 2017 times 0 is just 0. 2018. And then what we could do is, exponent rules, right? Ln e to the 0. Isn't that just going to be 0? Okay, so even if we decided to write this step out again, something like this, ln e to the 0, 2018, pull out that 18 into the front, 2018 times ln e to the 0. That guy is just going to be, what is that? Isn't this just 0 as well? Right, so no matter which way you do it, there's many different ways, but you basically get the same answer no matter what. And so I tried this one. I'd like you to take a look through it. Ln 1 over e, so I just converted that into an exponent, make it a little bit easier. E to the ln 0.2, and so there was that property that if you take ln of a number and then e to the exponent of that answer, you're just going to get whatever that number was. And then writing out that root as an exponent instead makes it look a little bit easier. So let's do this in a different color, taking this guy, bringing it down, okay, it's right here, multiplying, ln e. Now, you're not subtracting 1, this isn't the power rule or anything like that, we're just simplifying using log rules. Okay, converting this guy into a fraction, and then bringing this guy down in front, So we're going to multiply to that 3, and we'll still have ln e. Both of these guys are going to equal to 1. And so we're just going to simplify it and we get negative 13 over 5. Okay, so I did want to show you something with the graphing calculator in a second. We do know that the derivative of e to the power of x is e to the power of x. And so let's talk about the derivative of any exponential function. So we had seen that before, that any of these guys, their derivative is going to be the exact same thing. And we saw this in the last video. Okay, so y prime, y prime, y prime. Except they were all multiplying some sort of a k value, right? This one was a certain k, this one was a certain k, and multiplying a certain k. And so what exactly are those? So what I'm going to show you is through a graphing calculator, I might be able to shed some light on what those k values are, even though you're totally peeking and it's right here. Okay, so what I'm going to do is I'm going to grab a calculator and I'm going to write down, I'm going to take the menu, an action, and I'm going to define what g of x is. So let's just use 2 to the power of x. We'll do that first one. Okay, so now the graphing calculator knows that g of x is 2 to the power of x. Okay, now what we're going to tell it to do is we want to take the derivative. So we're going to go to calculus, take the derivative of g of x, and so it already knows what g at x is with respect to x. And look, so the derivative is the original function multiplied by ln of the base. So that's what I have here, that every single derivative is the original, which is in blue, times ln of the base. And so if I decided to just give you a rule, what you have is anything to the power of x, taking the derivative would be ln of the base times a to the power of x. And so it would be whatever the original was times ln a. The reason why I have a 1 here is because the 1 is if I decided to take the derivative of the actual function here. Because if you then have a function inside, what's going to happen is you have the original, which is right here. You then have ln a, but you also have to do a chain rule and multiply whatever the derivative of that function is. Okay, so we have the simple and then we also have the chain rule. So let's continue. We're going to do example number 3. Example number 4, I'm sorry. Find the equation of the tangent to y equals 4 to the power of x at x equals to 3. Okay, so the first thing I want to do is I want to find the derivative. Okay, y prime is going to be the derivative of 4 to the power of x, and so we said that that was the original multiplied by ln of the base, which was 4. Okay, so that's the derivative. Now you want the derivative when x is 3. Okay, so you're going to go y prime at 3 is equal to 4 ln 4, but with the 3 right here. Okay, and so what is that equal to? 64 times ln 4, and then we're just going to leave it like that because I don't want any decimals right now. 64 ln 4 for now. It does, you know what, it doesn't actually say it, but I'm just going to make it an exact equation so that you use no decimals. All right. Now the next part is you probably need some sort of a point because you're going to sub it into your x and y, because you have y equals your slope (64 ln 4). That's your slope. X plus b, and so you need your x and your y to sub it in, right? And you guys knew that your x is 3. You just need to find a y. Okay, so you take your original equation off to the side, and you plug in the 3. And so y is 64, which means that there's a point at 3 and 64. Let's put that in. There's your 4, there's your 3. 64 times ln 4 times 3 plus b. Okay, and you can pull this guy out because this is like together, right? So why don't we just multiply that together? And we get 64 is 192, and leave the ln 4 together because technically those guys exist together. Kind of like a trig, like sine 4 degrees or something. All right, and we're going to just bring that all to the other side. 64 minus 192 ln 4 is your b. That means that your equation of the tangent is y equals 64 ln 4x plus 64 minus 192 ln 4. So that would be the exact. If you really want to, you can convert these guys into decimals if they say that you can have an approximate answer. Okay, so let's get some word problems in there. A biologist is studying the increase in population of a particular insect in a provincial park. The population triples every week. Initially, there are 100 insects. Assume that the population continues to increase at this rate. So determine the population after 4 weeks. Okay, saying that they triple every week gives you the base. That is the rate at which it increases. Okay, and they also gave you the initial population, which goes right in front, to the power of t for the 3. So if you want 4 weeks, you're going to then enter 4 into your time, and you're going to solve for the answer. So the population of insects is 8,100 in 4 weeks. The next part asks you for a rate, because they want to know how fast is this growing, which means you want p prime. And it says when it was first discovered, t is 0. You should see that like a lot of these questions, these derivative questions, are very similar. Okay, so take the derivative. Now, taking the derivative means you can kind of use this as a product rule. Okay, derivative of the first times whatever the second is. All right. That's just going to give you 0 because the derivative of 100 is 0. Or taking this entire thing, not touching it, and taking the derivative of this guy. Okay, which is the derivative of 3 to the power of t is still 3 to the power of t, but multiplying that ln 3 part and multiplying the original 100. This is what you're going to get after you do a product rule. Okay, now you're going to sub in 0 into your t and get an initial, when it was first discovered, the initial growing rate. And so the population was increasing initially when it was first discovered at 110 insects per week. So I have a last question in here. When does the rate of growth of the population reach 8,899 insects per week? So when they say when, they're looking for time. And they've given you the p prime. So I've subbed it into p prime, and using the same equation, I'm now going to solve for t. So notice that t is locked away in here. I'm going to bring everything else to the other side first. So why don't we divide out that 100 and the ln 3. I can do that because all 3 of these guys are multiplying each other. So these will go away and these will go away. Only, again, because all 3 terms on the top are multiplying each other. But you got to do the same to the other side. So you end up with the next step. The only thing left on the right-hand side is 3 to the power of t. And then you have this fraction on the other side. Now, since t is locked away all the way at the top, I kind of want to do a ln of both sides because that'll help me to bring the t down. And now t is multiplying. So that's much easier to solve for t now because it's not as an exponent anymore. Now what I'm going to do is divide out both sides by ln 3. And so I come up with a ginormous fraction that I can then enter into my calculator and get approximately 4.00002. That means after 4 weeks, the population reaches a growth rate of 8,899 insects per week. I'd probably just round that to an even 4 weeks. Okay, so this was like a huge recap of log properties. Notice that they're very similar to ln, which is then just log to the base, I can't even speak anymore, log to the base e of x. And that is, again, something that's related to our exponential derivatives.